So we have a small charged sphere. We're treating it as a point charge of charge Q. And a mass M is hanging stationary. It's a very important part of this. From a massless string attached to a long wire with a uniform linear charge density lambda. The wire is vertical up from the ground. We will include gravitational pull of Earth in this problem. The string has a length of L and makes an angle theta with the wire, and these are our nodes. So what is the charge of the sphere? Well, this is like a physics 1 problem using physics 2 ideas. So when we're doing like something like physics 1, we always start with a free body diagram. So I'm going to create a free body diagram. Free body diagram. And we're talking about the mass M for this little, this little charge here. We're talking about that, so we're going to use a free body diagram of this. So I'm going to draw my point charge, little sphere, call it M. Now we need to talk about what is, what things are affecting M. So we have mg, or gravity, pulling it down. And then I have Fe pointing this way. Well, you're asking like, well, how do you know this? Well, let's talk about the rod here first. So the rod here has some positive charge that way. So off this rod, we have some electric field pointing away from it because it's positive. Well, the mass is, it's not moving at all. Therefore, this Fe is pushing that charge away to keep it from, swinging backwards. Because if it wasn't, let's say I was pulling on it, it could pull on it, but that would just affect what kind of charge Q is. So just realize that. This is a positive charge, therefore it's pointing this way. And it's not moving, so it's pushing that way. So you have the Fe pointing that way. Now, let me clean this up. We have some tension force along this. We're going to call it T. So we have big T. Now we need to talk about our Cartesian coordinate system, or what coordinate system we're going to use. Well, it's a 2D object, and we're talking about a 2D, something in 2D. So we're going to use a Cartesian coordinate of this is my y, and that's my x. So let's talk about what things are in my x and what things are my y and what's not. Well, this mg down here, it's all in the y, so we're good there. This Fe, it's all in the x, so we're good there. Well, this t right here, it's not all in the y or all in the x, so we need to create it all in the y and all in the x. So how do we do that? Well, we have some, t in the x here and some t in the y here. Now, obviously they line up appropriately. I'm just drawing it so we can see it here. And then we have some theta here. So it literally looks like this. We have t in my x, comes all the way here, and you can't see, but it's on this line here. That's my t of my y there. So let's go ahead and erase that. Clean this up a bit. Perfect. Now we have everything we need. We have our tx, we have everything our x's, we have everything our y's. So now we need to go into F equals ma. Well, we don't have just all in one or all in the other, so we have to do our f of x and our f of y equals the mass times the acceleration in our x times our mass times our acceleration in our y. All right. Now let's talk about what things are in our x and what direction are they pointing. Well, we have here, I'm going to highlight it, we have our Fe, okay? Well, our Fe is pointing in the positive x direction, so a positive Fe. And then I have, let me highlight it for you, this Tx. And which way is our Tx pointing? Well, it's pointing in the negative x direction, so the negative Tx. All right, well, now I have a negative mg plus a ty. And so you should be able to see where that's coming from. This mg is pointing all down in the y, and this ty is pointing all up in the, y direction. All right, let's clean this up. Now we have to consider, is there any acceleration in our x, any acceleration in our y? Well, it's not moving, it's stationary. So no, this is 0 and this is 0. So this whole thing is 0. This whole thing is 0. So we have 0 equals fe minus tx, and 0 equals negative mg plus ty. All right, well, let's clean up a little bit. I want to equate things. So I have tx equals fe and ty equals mg. And you see how I built this. I took this, brought it to this side, took this, brought it to that side. Super simple. All right, well, we need to relate these two equations. Right now, there's something that I can plug into the other. Well, let's talk about our t, right? I'm going to draw this nice and clean for us. So this is our t, this is our theta, this is our tx, this is our ty. Perfect. We can relate ty and tx together via the tangent of theta equals opposite over adjacent, which equals, let me scoot that over so you can see. Sorry if it kind of cuts it off. I had to fix OBS and everything for it. It's kind of a pain in the butt. So hopefully this, I didn't cut anything off. So what is our opposite? Well, our opposite is tx, and our adjacent is ty. Therefore, tx equals ty tangent of theta. Well, do we know what ty is? Yeah, of course we do. We know ty equals mg. So tx equals mg tangent of theta. So let's clean up a little bit. I'm going to zoom out so you see what's going on. Oh, I don't know why I just did that. I'm sorry. So we're going to plug this into here, and I'll work down here. So we get mg tangent of theta equals fe. Perfect. Now when you say, okay, well, none of this has anything to do with q. Remember, we're trying to find q. Well, remember, fe equals qe. So let's plug qe in for fe. So I have mg tangent of theta equals qe. Well, we're trying to solve for q, so let's just solve for q. mg tangent of theta divided by e equals q. Perfect. Now you may be saying, all right, we're done. Well, we don't know what e is. E isn't like some, it's not epsilon naught. It's not something that we know. So let's solve for e. So how do we solve for e? There's two ways to approach this. There's Gauss, and then there's the other way where E equals K dq. We're not worried about that. We're only going to worry about Gauss. So when you come across this problem in the test, Gauss. Gauss is your way to go. So let's do this. So I have my rod here. It's some lambda. Remember, some lambda. I'm not going to draw the arrow, so it's a little clean. All right, now we need to pick a Gaussian surface. I'm going to do that in green. So my Gaussian surface, it's going to go this way. And that way. Perfect. Now it's a cylinder, obviously. Well, not so obviously. I'm not the best drawer. Anyways, that's our cylinder. Now, what is our radius, our R here? Well, our R, let's look it back up to here. We have to think about this as, what are we enclosing? Well, we don't want to enclose this Q here. So the maximum this can go is R equals, so we have, I'm so sorry. Let me draw the triangle. This is L, and that's theta. So I'm going to draw it nice and clean over here for us so we can see it. L, R, theta. So we can say the sine of theta equals R over L, where R equals the sine of theta times L. So I'm just going to, put a block around this because we are going to need that later. But if you want to talk about this later, up to you where you want to address this. All right, now let's talk about our Gaussian. So what is our Gaussian equation? Well, it's Q enclosed divided by epsilon naught equals the closed integral of E dA cosine of theta. You can also write it as the E vector dotted into the dA vector, but it's just E dA cosine of theta. Well, what do we need to be concerned with here? Well, we need to be concerned with the sleeve, so like this part around here, and we need to be concerned with our caps. Okay. Well, if we think about it, our normal vector, I'm going to call this my normal vector on these caps here, right? When we talk about our electric field is going to point every which way around this thing, right? Because we're going to have, this is going to point off that way, and then towards us, and then away from us, whatever way. It's going to point off in all those different directions, but all these directions are 90 degrees no matter which way you talk about it. Therefore, in the cosine of 90 degrees equals 0. So our caps, they kind of go away. We don't need to be concerned about our caps because our caps are 0. They're just 0. So let's not worry about our caps. Now let's talk about our sleeve. Our sleeve, and the reason we chose this Gaussian surface is, let's draw our electric fields. So we have it that way, going away, coming towards us, going away from us. X's are, into the paper. Circles are, towards us. Kind of imagine it that way. They're coming off, that way, every which way. The normal vector on this outside is the same as the electric field at every point. So this is my normal. Therefore, the cosine of 0 equals 1. And our electric field is the same everywhere, so we can pull the electric field out. So we can say Q enclosed divided by epsilon naught equals E times the closed integral of dA. Awesome. Well, what's the closed integral of dA? Well, it's the surface area of our Gaussian surface sleeve here. Just the sleeve, because we're talking about just the sleeve for this part. Technically, we have a +0 and a +0 for the caps, right? But we're not talking about that. We're talking about the sleeve. Well, what is the surface area of the sleeve of a cylinder? Well, it's Q enclosed. Let's write out Q enclosed divided by epsilon naught equals E 2 pi R L, where L is the length of the height pretty much of our Gaussian surface. So R is the sine of theta times L, remember? So let's go back and let's just talk about Q enclosed now. So Q enclosed, by the way, this L is, I'm not going to call it L, I'm going to call it H. It's the height, and the reason I'm doing that is just because we have this other L here with our R sine theta L, and I don't want to confuse that L and this L, so we're going to call it H. Awesome. Now we're talking about Q enclosed. Well, what is Q enclosed? Well, remember, lambda equals Q enclosed divided by the length of the rod. So I have Q enclosed equals lambda L. But if you remember, the L of this rod here, Sorry, this is like a mess at this point. The L of this rod here is also the height because they're quote unquote very long or infinitely long. So this is just H. Let's plug it in. Lambda H divided by epsilon naught equals E 2 pi, and R is the sine of theta L, and we also have that H. Well, there's an H on each side, so they're going to go away, and we're going to solve for E. E equals lambda epsilon naught 2 pi sine of theta L. Awesome. Now we need to take this and we need to plug it back in for where exactly? Right here to this. So let's go ahead and do that. So we have mg tangent of theta divided by this E divided by lambda divided by epsilon naught 2 pi sine of theta L equals Q. Now this is the final answer. You can clean this up if you would like. I don't know if you have to. I don't think you do. But this is really your final answer. But you can copy dot flip and say mg epsilon naught 2 pi sine theta L divided by lambda equals Q. Whatever you feel best with, go ahead, go that route. But this is how you approach that problem. Let's kind of go through the steps one more time of how do we approach this. First thing we did, we realized, okay, well, this is a physics 1 problem related to physics 2. So we always draw a free body diagram first. Then we put everything in terms of our coordinate system. So we chose an X and a Y coordinate system. And then we related our TX and our TY together using that theta. Then we had mg tangent theta equals Fe. Remember, Fe equals QE. Then we had to solve for E. And the way we're going to solve for E on these problems, when we come to the test, we're going to use Gauss's law. Use Gauss's law. That's what the professor said. We're going to use Gauss's law. We're going to use Gaussian surface and really just plug and chug. That's all there is to it at that point. But this is how you approach problem 1. If you have any questions, leave them in the comments. I'd be more than happy to answer them. Thank you.